screen. Can everybody hear me? Is it all good?
Yes.
Okay. So I will present to you my work on nonlinear lattices of granular aluminum resonators done in the NS2 group under the supervision of Jérôme Estève and Julien Gabelli, as well as Marco Prilli. So the goal of this thesis is to create and simulate arbitrary Hamiltonian of photons. We have a set of sites that will hold photons at a frequency omega. Those sites are coupled with a hopping rate J. And in each site, we expect we have a nonlinearity U that gives the interaction of the photons between themselves. Such a framework has been extensively studied with photonic lattices. We have, for example, an example of the helical waveguides coupled to each other evanescently, and in a honeycomb structure, reminding of the honeycomb structure of graphene. It's possible with such systems to create a band structure for photons. In photonic lattices, such as this one, there's no interaction. But you can also, with semiconductors and a setup called microcavity polaritons, in which each of the site corresponds to a pillar that holds a photon amplitude. You can connect those pillars and create as well a band structure for photons. In such system, you can have a small weak nonlinearity for the photons and work with nonlinear effects in a mean field way. Another framework that can be used to create such systems is based on microwave photons and superconducting circuits. Here we have two examples, one done in our lab with spiral resonators in a honeycomb geometry. Each resonator, like here, for example, is a spiral resonator. Here you have another type of sample with coplanar waveguide resonators. And those are made of superconducting circuits, and they resonate around 6 gigahertz. And you can couple those resonators with the capacitive and inductive coupling in the 100 megahertz up to 100 megahertz range. And you see that you have very good scalability with this technique. It's possible here to create a lot of resonators in enclosed space. Here we have up to 324 resonators in this sample that was 1 centimeter wide. And here you have 49 resonators of a 3 centimeter size sample. Another advantage of using superconducting circuits is the possibility to implement very strong interactions with a Transmon qubit consisting of capacitance and a nonlinear Josephson inductance. Here you have an example of a capacitance interdigitate capacitance shunted by a Josephson inductance, and you can bring the nonlinearity to amplitudes around 300 megahertz or more. Here's an example. Here we have an example with a different design, but the same principle of Transmon qubits next to each other, creating a 1D line of sites with a very that will be in a strongly interacting regime. This setup was used to show the multi-insulator for photons. It's possible to excuse me. The advantage also is that we can modulate the nonlinearity of our resonators by changing the nonlinear element. We can, for example, change from a Josephson junction to a Josephson junction array, or even replace the inductance with a high kinetic inductance superconducting wire. with the kinetic inductance will have a lower nonlinearity as the Josephson inductance, and we can go from a strongly interacting regime down to a weakly interacting regime. In our setup, we will use those wires, and now we aim to create a lattice in which each site will be one of those resonating structure with weak nonlinearity. We can couple, we aim to couple the sites with a coupling around 200 megahertz, creating a band structure in microwave regime with a weak nonlinearity around the kilohertz. We aim to create a design in which we will be able to first characterize this lattice with a weak nonlinearity in a mean field regime of photons, and in the longer run, be able to replace the nonlinearity by the inductance with a very highly nonlinear Josephson inductance without changing the design. Go up to a very strong nonlinearity up to 300 megahertz. One of the phenomena that can occur in such a system is thermalization to the nonlinearity and possibly Bose-Einstein condensation. If we have an excitation in a square lattice with a density that is shown here, and we expect that through the weak nonlinearity they will thermalize, the resulting distribution will be Bose-Einstein, and if we reduce the temperature of this distribution, we expect a condensation of the photons, and where they will coalesce towards a specific point of the spectrum. The outline of this talk will be to show how we characterize the single resonators and their nonlinearity. We will then show the way to design lattices of multiple of those resonators. We will then characterize the interactions between the photons in one of those lattices, the rectangular lattice. And we will talk about the dynamics and the thermalization in the same lattice. So first with the characterization of single resonators. So as we talked before, we can create a transfer setup in which we have two capacitive pads shunted by an inductance. In this first case, a Josephson inductance. This Josephson inductance is nonlinear with a current, and we can compute the nonlinearity based on the parameters of the resonators. And we find that it only depends on the global parameter of impedance of the resonator. And we don't have another way to change the nonlinearity of such a system. By replacing this wire with a high kinetic inductance material, we can create a weakly nonlinear resonator. High kinetic inductance material are materials where the resistivity is much higher, and thus will have a very high kinetic inductance due to the fact that the carriers have a mass and that create a kinetic inductance. We can compute with the Matisse-Bardeen theory the link between the resistivity and the inductance of a wire, and we find that it is proportional. The inductance is proportional to the resistivity and inversely proportional to the gap. As we increase the current in the wire, we will create more depairing in the superconductor, and thus we will lower the gap of the resonator of the inductance, and thus we find a link between the current in the wire and the inductance of the total inductance of the wire as such, with a nonlinear current parameter I star, which is linked to the critical current of the wire. Here we see that the critical current is linked to the section of the wire multiplied by the density of current JC, and thus we can modulate the nonlinearity in the same way as before by changing the global parameter, but also by changing the critical nonlinear current I star of the wire. And thus we have two ways to increase, and we can shift the nonlinearity of the total resonator by orders of magnitude by changing the section of the wire. In order to assess this link, we fabricated multiple resonators with ranging sections of the wire. In order to evaporate, we chose as a inductance, high kinetic inductance material, the granular aluminum. And in order to evaporate this, we perform an evaporation with a high pressure, with a pressure of oxygen around 10 to the 5 millibar, and we try to keep the lower pressure at a low pressure in order to not contaminate the crucible. And if we change the pressure of oxygen, we see that we can increase the resistivity of the material. We see that as we shift the pressure of oxygen by only a third or even a tenth of the value, we can change by orders of magnitude the resistivity of the end sample, which makes it complicated. In order to measure the nonlinear dependence of with the section, we perform multiple transmission measurements of those resonators with ranging cross-section from only 400 nanometer times 10 nanometer up to 5 micrometer wide resonators. And we perform a transmission, and as we see that as we range the power of input inside the microwave line that is coupled to our resonators, we shift the frequency, and we see a Duffing shift of the transmission. We can fit this shift with a nonlinear equation of the field inside the resonator and extract the nonlinear parameter U of each of those resonators. And we see that with the different samples, we are able to find nonlinearities that range from only a few hertz up to tens of kilohertz. In order to compare those values, we compute the critical density of current of each of those wires with this equation, and we can compare it to a standard that we measured onto one DC measurement of one wire of the critical density of current. For each of the resonators, we compute the expected critical current, having a measurement of their resistivity, which is shown below, and we compare it to the critical nonlinear current density of current J star, and here are all the measurements in blue, and we find that there is a link between the two around 2.4. Around 2.4. Sorry, there's a mistake. Thus, we were able to find a good agreement between the expected density of current of nonlinear current and the expected critical current of each wire. Now, we want to create lattices of such resonators. Thus, we can design a lattice where each of those resonators are coupled to the next capacitively. If we consider each pad a node at uniform potential, which are connected to the other pads with a capacitance, we can simulate the capacitance between the pad using a software simulation Sonnet and compute the equivalent circuit of such a lattice. If we add an inductance between each of the pad, each cell, we can compute the band structure of our lattice, and we find that such a set of sites coupled to each other is such a set of resonators coupled to each other will be equivalent to a band structure with sites around 6 gigahertz and a coupling of around 200 megahertz. There's other possibilities to engineer various band structure. Here we can, for example, create a band structure with a cell that has 2 resonances and 3 capacitive bands with the equivalent schematics shown here. Thus, we have 2 bands linked with the 2 resonances in each cell. And we see that if we take the plaquette shown here, we can write a localized mode that will solve the electrocinetic equation of the lattice and give a set of localized modes that will form a flat band over the infinite lattice. And thus, one of the 2 bands is flat, and we have the second dispersive band at the top. We fabricated the 2 samples of which I showed the design. Here, first, the rectangular design. Here, we fabricated a sample with 800 sites, for which we couple at the edges. We perform a transmission measurement through the sample in a cryogenic setup, and we measure, for example, for the transmission to the 1 and 3 ports and 1 and 2, a set of resonating frequencies. We also perform an automatic resistance measurement of each of the resistance sites, and we can compute from this resistance map, which is shown here, which has around a 10% dispersion overall because of a gradient in the y direction, but only a 2% dispersion in the x-axis. We can compute the expected inductance of each of the wire and compute the expected theoretical resonance of the entire lattice. We can compare this theory with one adjustable parameter, which is the main average amplitude of the inductance, to the mode density measured in transmission through multiple ports. And we find a good agreement of the measurement of the mode density as well to the theoretical density. We also fabricated a leap sample here with a slightly different geometry, but the same plaquette geometry and the same expected flat band. And we perform a transmission measurement. Here is shown for the 2 top nodes, in which we see a high density of mode in a small section of the bandwidth. And we can compute in this, we can measure in the same way the density of mode per megahertz and compare it to a theoretical computation in which we add various amount of dispersion of the inductances. Here we see that we find a good agreement with the theoretical values of frequencies if we take a 4% dispersion of the inductances of the lattice. So we found that it was possible to fabricate and design lattices of resonators. We will now go on to characterize the photon interaction in the rectangular lattice that we showed first. So in our lattice, if we go in the modal description of the lattice, we have the Hamiltonian, in which we have the linear evolution of each of the modes and a nonlinear interaction between the modes. The interaction can create processes at a phase matching condition between those modes, and we can separate those processes between the processes with only one mode, or the self-care, and then an interaction between two modes, the cross-care interaction, and then when we have 4 different modes at a phase matching condition, we can find a 4-wave mixing term. We perform first measurement of the transmission of each of the mode as we increase the power and find a Duffing shift equivalent to the single resonator measurement shown before. And in the same way, we can fit each of those Duffing shift with the equation of the nonlinear equation of the mode at each frequency. And we can extract the diagonal term of interaction between the 4 modes selected here, which we find amplitude of self-interaction around 900 Hertz. Now we can measure the cross-care interactions between each of the modes. each of them, if we select a mode P that into which we drive at a high number of photons, this will be equivalent to shifting the frequency of the mode N. Here we have a measurement of the transmission of mode N. In color is shown the measured amplitude of photons into a different P, and we see a shift. And if we fit the shift and link it to the number of photons in P, we find a variation that is linear with the amplitude of photons. If we do this for the 4 resonance shown in the previous slide, we can find a non-diagonal cross-care interaction between those terms. It's interesting to note that they are much lower, which is consistent with the fact that the interaction will be linked to an overlap of the mode structure over the lattice, contrary to a single square amplitude of the mode structure for the diagonal terms. Now we can try to measure the 4-wave mixing process. Here we can fill 3 modes, 2, 3, and 4, with a high number of photons, and measure the expected and measure the number of photons in the first mode, which are exact phase matching condition. If the amplitude of photon expected in the first mode for the number of photons in all the 3 modes is given by this equation, and with a loss of around 1 megahertz and a number of photons in each of the input modes around 1,000, as well as a nonlinear interaction U of around 10 hertz per photon, we expect only 0.1 photon in the output mode. We can measure this output with a very low bandwidth at the exact phase matching condition, and we can relate the measurement, the power output to compute the number of photons in this output mode and relate it to the square root of the number of photons in each of the input modes. We find a linear relationship between the square root of the output photons and the square root of the input photons. And we can find a nonlinear interaction between the four modes of around 5 hertz per photon. If we drive at higher amplitude, it's interesting to see that we can create processes in which the pump will separate into multiple frequency peaks. These processes happen at amplitude around 1,000 times higher than the amplitude in which we measured the depthing shift or the previous measurement. And we find that the nonlinear interaction can create a set of symmetric symmetric output given frequencies. If we drive the lattice at even higher amplitudes, we can see that the mode structure breaks, and we have a chaotic output in which no specific frequency is discerned. Now we can talk about the dynamics of thermalization in a rectangular lattice. So in our lattice, we have, again, the Hamiltonian, in which we have the linear evolution of each of the modes, as well as the nonlinear interaction. This Hamiltonian conserves the number of photons. And it's interesting that if the nonlinear term brings the photons in the lattice to a thermal equilibrium, we expect an equilibrium distribution of Bose-Einstein. And this equilibrium distribution, if we drive it, if there's a high temperature for the photons, will go towards Rayleigh-Jeans distribution. if excuse me, in such a setup with the Bose-Einstein distribution, we expect a condensation of photons. Here for lattice, a rectangular lattice, we can measure the spectral density of photons over the lattice as we reduce the temperature of the distribution, and we expect a condensation of photons at a specific frequency. Now, if we try to compute the equilibrium distribution if we try to compute the critical temperature for varying density of photons in a rectangular lattice, and we vary the density of photons in this lattice, we can see that as we lower the density of photons, with the rectangular lattice, we will go we will cross over between two regimes in which, at a high number of photons, our rectangular lattice will have a density and a critical temperature which is equivalent to Rayleigh Jeans to the Rayleigh Jeans value for 3 classical photons. And as we reduce and we cross over below the 1 photon per site amplitude, we see that the critical temperature associated with this critical density will be equivalent to the critical density of Bose-Einstein 3 photons. Now, the next question is it possible to measure such a variation of the amplitude of the photons in our lattice? So we have a lattice system in which we measure the loss rate for each of the modes. Here we have an example of measurement in which we drive one of the modes with a high amplitude. And as we stop the pumping, we can witness the lifetime of the mode. We perform this measurement for multiple modes of the lattice, and we find an average lifetime of the photons in our lattice around 1 microsecond. So the question is it possible to have a thermalization time that is faster than the loss of photons in our system? We can perform a simulation with an equation of motion in which we have the linear evolution of each of the mode and the Kerr interactions. Each of the Kerr interactions is related to the amplitude of current onto the lattice. And if we fill half of the modes of our lattice with the ranging number of photons per site from only 700 up to 2 to the 4 photons, we see that as we increase the number of photons, the entropy of distribution thermalizes faster to equilibrium and gets to a Rayleigh Jeans distribution. And this equilibrium is reached in microsecond for an amplitude of photons around 1,500 photons per site. This simulation was done with the amplitudes expected for the rectangular lattice nonlinearities. Now, what do we expect to measure in the context of our lattice? Our lattice has a band structure that we showed before here. We have a top of the band structure, which has negative mass, and the photons in each site have a negative interaction. Thus, if we perform a simulation in which we fill the modes at the top part of the band, we expect the nonlinear interaction to bring the photons toward the top of the band, and after a certain time to stop to only get to an equilibrium distribution function. in order to try to measure this phenomenon, we select a portion of the transmission of the rectangular lattice. Here's a zoom of the transmission of the rectangular lattice with the top ports shown before. And in each of we can select a different resonant mode of this lattice. And we aim to drive this system at those specific frequencies with a high number of photons during a certain time. And after this time, we stop the pump, and we expect to have initialized the system with a high number of photons in the selected mode and witness the dynamical movement of the photons in the lattice. Now we have to create a setup of to fabricate this pumped frequency comb. Thus, we used a digital analyzer converter that of 4 gigahertz bandwidth. Is an example of a measurement of the output of this DAC, in which we can create an arbitrary set of peaks. And we, in order to bring this 4 gigahertz bandwidth towards the bandwidth of our lattice, we mix it with a source at a higher amplitude than our lattice, around at 7 gigahertz. And we can drive the amplitude of the source up and down, and thus create a setup that will have a set of frequencies with an arbitrary amplitude and frequency within a 1 gigahertz band or more. And then we can drive the amplitude up and down in order to initialize the system. Here is an example of a measurement in which we use the set of frequencies shown before. We input amplitudes to the top ports, and at the output with a spectral analyzer, we measure at different frequencies the output of the lattice. We see that we can, the frequencies, during the time of the pumping, we have a high output amplitude linked with photons being in the lattice at these specific frequencies. And as we stop the pumping, we see the dynamical evolution of the lattice. If we select a varying peak amplitude of the comb structure, we see that from a low amplitude, here corresponding to an amplitude below the B stability of the duffing of each mode, we only measure exponential decay at all of the frequencies that we can measure. And as we increase the amplitude of the comb, we witness non-exponential decay of the amplitude at different frequencies, linked with nonlinear interactions in our lattice. An analysis of the amplitude output of the lattice tells us that we expect to have, even at maximum amplitude, only around 400 photons per site, which is well below the threshold used that would give thermalization within 1 microsecond. We also witness that the loss rate and the photons are lost at a higher rate than at lower amplitude, which we cannot explain easily and remains a topic of experimentation. In conclusion, we found that we were able to create single resonators with varying nonlinearity up to only a few hertz, up to 10 kilohertz. We were able to fabricate lattices with those resonators, and we're able to fit the mode density measured on this lattice with the theoretical measurements of the of the resistances, and we were able to characterize the nonlinear lattice processes in this lattice. The perspective in the next steps for this project would be to understand and observe thermalization in the lattice, first by reducing the coupling between the sites and thus increase drastically the density of modes, which would increase the interaction in the lattice. Secondly, we could improve the lifetime of the lattice, which will reduce the threshold in number of photons and help observe the dynamical evolution. And last, if this first step is possible, we can replace the granular aluminum wires with Josephson junctions and try to go towards a quantum regime of condensation in our lattice. I would like to acknowledge I have a lot of acknowledgements to do. First, I would like to thank my advisors towards these many years in the lab. I would like to thank the people in the NS2 group, Marco, Frank, Julien, Caris, and all the previous PhDs that were present in the lab. I want to thank especially Raphael and Sylvie of the Nano service, as well as the rest of the people in other groups, such as the group and the rest of the staff at the LPS, as well as acknowledge the collaborations we did with other researchers in Grenoble. And finally, I would like to acknowledge my friends, which were very helpful, my family, and especially Claudia.
Okay, thank you, Mathieu. So now we propose that so we'll the series of discussions with the members of the jury. So the tradition is that we start with the two referees. So Martin, I propose that you start, if you don't mind.
No, it's fine. Mathieu, thank you very much for the nice talk. Hope you can hear me. So maybe to start, could you explain why you mentioned your talk, but could you explain again why have you chosen that particular superconductor?
Yes.
Yeah, it's actually a couple of questions. So first, why have you chosen granular aluminum? Why was that your choice?